So this example, I wanted to give you guys yet another example of me solving a modeling problem for you. So in this course, we're in the middle third section. The focus of this middle third section is to do lumped parameter modeling, where we say, okay, this is like a mass, this is like a spring, a damper, etc., of electrical systems, mechanical systems, rotational and translational, all separately. In the third part of the course, the third section of the course, we're going to learn how to do them mixed together, so electromechanical type systems. But we need to get some practice doing these. This is seeing many examples is going to help. So this example is going to be one of many that you will be seeing over the coming weeks. And let's do a rotational mechanical lumped parameter model of the following system. Let's look at a DC motor, say like a brushed DC motor. It doesn't matter in this case because we're not going to model the electrical side, but DC motor, shaft coming out of it, and that shaft needs to connect to another shaft that is going to be supported by some bearings. We're looking at it from above maybe, so below this it would be supported. And then the shaft goes through the bearing and it's connected to a flywheel. For now, we'll just have it be a flywheel. Maybe later on we'll be able to model this as maybe there's a gear that's connected to another mechanical system, subsystem. But for now, we'll just say it's a flywheel. And there's maybe a bearing on this side as well. So we'll put the bearing in here. And that'll be the termination of this shaft. So these two shafts are going to get coupled together with a shaft coupler. Okay, so maybe it doesn't look quite that big, but a shaft coupler. And we'll talk about a shaft coupler for just a moment because it's a component that you may not have seen before. A shaft coupler is there, first of all, to transmit torque through it from one shaft to another. Pretty much what you'd expect it to do when it couples the two shafts together. But it has to do that in a way that's pretty special because these two shafts are never perfectly aligned. So if you spent any time trying to build stuff in a machine shop, you know that nothing is ever perfect. It's only as close as the tolerance tells you it's going to be. So it's very challenging to get two shafts to meet up perfectly parallel or even very parallel and not offset at all. So there are two ways it can go wrong. You could have the shaft offset at an angle. So like one shaft is this way, the other shaft is this way, say. You could have the two shafts offset also just translationally offset, so they're like this. These are both pretty extreme in the ways that they're drawn, just to highlight the two ways that they can be off, right? Angle and just displacement. But in either of these cases, if you tried to couple these two shafts with a rigid element, if you could get them to actually mate at all, which is questionable, if you put like a collar over each one, try to connect them up, they might not even go together. if you did get them to go together and it's rigidly connected, depending on the extreme level of misalignment, if it's too misaligned, it will just literally just bind. You will not be able to turn the shaft at all. Think about what happens if you try to turn. So say you rigidly connected these two together, just totally rigidly connected them together. And you start turning this shaft. Say this shaft, you can turn it, it's the power shaft. This one's supposed to follow. Well, if this guy stays perfectly aligned with its axis, then this one has to be, as you turn it around, it's going to end up over here, right? So if I sort of mirrored that, this is where it would want to go. Well, it's supported by bearings over here. It doesn't want to move. That shaft doesn't want to move way over there. So it's going to resist that. So, it could bind. It could just totally break the coupler. It could break the bearing. It could crack the bearings. It could wear the bearings down quickly if it's just a little bit misaligned and still rotates. It's bad news. You can't rigidly connect those two shafts together with a coupler. So what you do is you put a shaft coupler on that's flexible. So this is a flexible. And this shaft coupler has a bunch of material removed in it so that when you have this misalignment, say, so usually it's got like a solid piece. Well, I'll slow down and draw it a little more carefully. It's got a solid piece on this end that fits onto this shaft, and it's got a set screw, usually, not always, set screw that connects it to this shaft. And it's got a solid piece on this side, too, that connects to this shaft, with a set screw or something. And in between it's usually metal. There are some that are other types of materials, but they're usually metal with a lot of material removed to give it more flex. Okay, so you see this sort of almost corkscrew cuts in the material in between, and this will flex. Let's try to do it smoothly. This will flex in between by essentially bending along these cuts. And the torque here gets transmitted here without trying to displace it too much. There is some spring action, and the more misalignment you have, even with a flexible shaft coupling, the quicker your bearings will wear out, but at least it won't bind up and you won't have like catastrophic failures. This coupler wears out too, depending on the material you use. Cheaper ones are made of aluminum. More expensive ones are made of steel. And steel, you guys will learn about fatigue in your machine design class, but fatigue is something that is a big deal with aluminum. Not as big of a deal with steel, as long as you don't overstress it. So keep in mind that, this fatigue of going through many, many cycles of cyclic loading is going to stress this part and will eventually wear it out and it'll fail. But this flexible shaft coupling is a pretty much a standard part for transmitting torque through from one shaft to another. So here's our flexible shaft coupler. We put it in here. We've got our bearings, the usual sort of bearing situation, and then the flywheel. bearings, let's say 2. Sometimes you'll see that like 2 or x2 or whatever, denoting that there are 2 of them on the drawing. So this is a sort of, really high-level schematic, but it's not lumped parameter modeled yet, because we have these things like, okay, we do have lumped parameter flywheels and bearings, but we don't have lumped parameter shaft couplers. So we've got to figure out what we're going to lumped parameter model that as. So let's draw a schematic that is fully lumped up for us. So we're not going to model this motor at all. We're just gonna leave it. It's a motor. Let's say we'll model it as an angular velocity source. Now, we could model it as an as a torque source as well. But it sort of depends on the situation. We don't have any reason to believe that it makes more sense to model it as an angular velocity source or a torque source. In a problem I would give you, I would just tell you. Later on, we'll typically model the electronic side of the motor, and so we won't model it as a source at all. So it's not too big of a deal. Later on, we'll just totally ignore this issue by modeling what goes on in the motor itself. The flexible shaft coupler. A pretty good model of it is a spring element. So an angular spring or a torsional spring with spring constant K. It's not a perfect model, but it's pretty good because it adds this flexibility to the shaft. So if you're worried about small displacements and transient responses that are happening quickly, this flexibility is going to be something you need to model. So if you're not worried about it, if you're like, I don't need precision, in the milliseconds time frame in terms of position, so I'm going to ignore the flexibility of the shaft coupler. That's a design decision to make in terms of what are you trying to design for. We'll treat it as being a spring in this model, just because it's sort of the more complicated version. You could get simpler if you wanted to. If you made this model and then you were like, oh, I actually don't care about the flexibility, you could just take K as being very, very stiff, right? And you could take K to infinity and see how your model simplifies down. Okay, so that's an option you have too. So this shaft is going to go through a bearing damper, which we typically denote in this sort of schematic form like this. And there are 2 bearings here. So there's a bearing on this side, there's a bearing on this side. Assuming they're the same bearing, why should we probably just lump these 2 bearings into one bearing element? The primary reason is that they share the same angular velocity. Okay, so this shaft is relatively short with a flywheel on it, as far as we know. So we aren't going to have any difference in angular velocity across this flywheel shaft portion. So if they're all at the same angular velocity, all the bearing damping torque will be the same, will be proportional to the same velocity. And the 2 bearings will be in parallel. You could combine their damping to simplify the model as B. If you had individual bearing damping coefficients, you could combine them in parallel to get B. If you had different well, if you don't have any bearing damping coefficients, then what you can do is you can just do a measurement to figure out what B is. If you're measuring B and you've got two bearings in there, there's no way to differentiate between which bearings, applying a certain amount of force or torque versus another bearing, so you should just lump them together into a single bearing. If these were on, if there was a bearing here that we were modeling and a bearing here, those would have to be different because they have this separation, a separating coupler that makes the two torques different. Okay. All right. Now we've got our flywheel, and the flywheel is going to have moment of inertia J, and that'll be our lumped parameter model here. So now we need to draw a linear graph model. So now we're moving from, I guess, like in the dynamic systems notes, from chapter 1 to chapter 2, which is about linear graph modeling. So we need a linear graph model. So I'll call this sort of step 0, linear graph model. And that linear graph model is something that, for a mechanical rotational system, will have an angular velocity reference or ground that's omega equals 0 is a good one. So we can start drawing in the nodes now. We have a J node, an inertia node, J. And that same angular velocity that the J node has is shared by the B node as well, which also connects to ground because it's a bearing damping, so B. We should probably draw in a positive direction here for our torque, which we'll use the right-hand rule for. And so torque is when I look at it this way, when you guys look at it, it's this way. So right-hand rule, just make sure you use your right hand. And thumb in that direction. So this is the direction of positive torque. We don't know, we aren't given any information about the angular velocity source, what direction it thinks is positive. It depends on the direction you connect up the terminals for which direction positive voltage creates in terms of torque. Let's assume that it is also in this direction. So we could draw it, I guess, this way, which would be omega s in that direction, which is in the same direction as our positive coordinate arrow. So let's draw the source then. So it has its own shaft, so its own angular velocity. And the direction of its arrow is going to be away from the node of application because we have the direction of omega s being the same direction as the positive direction of the coordinate arrow, and it's an across variable source. Angular velocity for rotational mechanical systems is an across variable, so we've got ourselves an arrow down here. So the drop in angular velocity from positive to 0 is given there. Okay, so now we've got the angular velocity of this shaft connecting to this other shaft, which has got the flywheel. So in between, we have this flexible shaft coupling K that we have modeled. So this is our linear graph. Now we want to do a state space model of this linear graph. So of this system and we're going to start with the linear graph model and go from the linear graph to the state space model. So the first thing that we do is, so let's go to our text here, and we'll look at the directions. So 1A is to draw the normal tree. So 1A is to draw the normal tree. And let's draw it in green here. Maybe this green. And we'll draw it superimposed on the linear graph. So I'll just put normal tree. Let me know if this is an issue for you, if you're colorblind in this green, let me know. The first thing when you're drawing a normal tree, so drawing the normal tree, we have a procedure for that too. It's right in the preceding lecture. We go through and we include different elements in. We have to respect these two rules as we go through. We can't create any loops, and we have to have every node be connected. So the first thing to do is include all nodes. Here's a node, we'll include that. Here's a node, and the ground is also a node. Sometimes we skip drawing in all the nodes because all the nodes are always in the normal tree, right? So, but it's good to practice to remember. Okay, then we include all across variable sources. The across variable in the rotational mechanical energy domain is the angular velocity. So the angular velocity source is included in the normal tree. And that's the only one we've got, so nothing else. The next one is to select as many as possible A-type elements. The A-type element for a mechanical system that's rotational is it's the capacitor and analog, which is J, the moment of inertia. So J. Boom. Okay. All right, so now we actually are done. And the reason we know we're done is that if we include B or we include K, we'll create a loop, right? We can't create a loop. That's one of our rules, so we know we're done. If we weren't done, though, we could include as many as possible D-type elements. If we included B, which is our D-type element here, dissipative element, it would create a loop with J, so we can't include it. And if we had still more out, we could include as many as possible T-types, which would be K, which we can't do that either. So we're all good. All right, so now we'll go back to black here, 1B. So we're back on the lecture 3.4 graphs to state space algorithm. So we drew our normal tree. Now we identify the primary and secondary variables. So primary, secondary. And the way we do that is we look at the passive elements and we say, okay, if it's in the normal tree, it's a branch. The primary variable associated with it is its across variable. So omega j. And if it's a link, so there's only one passive branch. So if it's a link, we include the through variable, which is the torque in this case. So Tk and Tb, the torque through the spring and the damper. The secondary variables are just the opposite. So the torque through J, the angular velocity of K, the angular velocity across B. So we have our primary and our secondary variables. The third step, C, is to identify the state variables as being across variables on A-type branches and through variables on T-type links. Now, if you wrote the primary and secondary variables out, then the state variables are a subset of those primary variables. Remember, across variables on branches and through variables on links are the primaries. Well, across variables on branches, through variables on links are the state variables too. It's just that it's the across variables on A-type branches and through variables on T-type links. So we just identify the A-type and the T-types, and those are our state variables. So primary variable, this is an A-type, so omega j. This is a T-type, tk. So our state variables are omega j and tk. We can identify the order of the system when we have the number of state variables. Do we know what the order of the system is then? It's just 2. It's the number of state variables. So, there we go. Now we've got D. D, define the state vector x, input vector u, and output vector y. So the state vector is x. It's going to be a column vector that contains the state variables in any order you choose. But once you choose it, you got to stick to it. Omega j tk, let's say, in this case. The input vector is a vector of all the input variables. We have how many inputs in this problem? We've got the source, right? This is the input is the angular velocity source. So one input. So omega s is our input, and u is a 1 vector. The output vector is the vector of all the variables that are interesting to us. We made up this problem. We get to make up what's interesting to us also. Let's choose, maybe we're interested to know what the torque in the flexible shaft coupling is going to be, because maybe we're worried about a failure. So maybe we take the torque through the spring. And let's also take the angular momentum of the flywheel. Call it Hj. And this, this is arbitrary. In the problem I would give you, I would tell you these are the variables of interest to us. Good. So those are our output variables in a vector form. All right. 1e. So we're down to EFG, which are the elemental continuity and compatibility equations, which are analogous to what we did in electronics, which were the elemental KCL and KVL equations. Okay? So we're going to do a very similar process in this next part, but we're going to be a little bit more specific about which equations we write. Elemental equations are the same. So we write an elemental equation for each passive branch. We're going to set this up in a bit of a tabular form here. So we're going to say the element. We're going to say the elemental equation. And then we're going to, later on down here, we're going to put in the continuity and compatibility equations as well. So I like to list my elements in the same order that I put the state vector. So I put omega j first, so I'll put j, and then I'll put k. This pays off later, just in terms of keeping things straight, but it's up to you. Then I also need to include my damper b. The elemental equation, let's use dot notation here because we have no I's, we have no currents because it's not electronic. So we can get lazy and we can use dots. Hell yeah. I love dot notation. So we can use omega j dot for the elemental equation for the moment of inertia is 1 over j tj. The elemental equation for the spring is Tk dot equals K omega K, which is a derivative of Hooke's law. And we have Tb, the torque through the damper, being proportional to the angular velocity across the damper. Great. So this was E. Then we have to do 1F, which is the continuity equations. And if you look at the instructions, it says, our recipe, if you will, it says draw a continuity equation for each passive branch. So it says branch specifically, which means it's in the normal tree, right? By drawing a contour intersecting that and no other branch. So we go up to our normal tree here, and we say, okay, I need to draw a contour, which let's take purple here maybe. And I needed to draw a contour that intersects this branch for J, because it's a passive branch and no other branch. So this contour works, right? Now, when you take a contour to just be around a node, like we did here, this is going to look just like a KCL equation. It's just like a node equation. Everything that goes in has to come out. If you sum up everything that goes in, it has to equal 0. So it's just like a KCL equation, but with the through variable in this case of torque, Tj. So if we were to go sort of old school and say, okay, let's say everything going into this contour is positive, then we would say Tk goes in, Tb leaves, and Tj leaves. So minus Tb minus Tj equals 0. The instructions then say to solve for that secondary variable associated with the branch, okay, which is, in this case, Tj, right? So Tj is the secondary variable associated with the branch. Here's Tb, and then here is Tk. So we want to solve for Tj. So this would say that Tj equals, so Tk minus Tb, right? So that's one way to go with it. That's our continuity equation. I prefer to use a sort of shortcut here. I know that I need the through variable associated with the branch, which is j in this case. I need Tj on the left-hand side of my equation. Yeah, so what I say is, okay, Tj, since it's leaving, it has to equal everything that goes in minus everything that goes out except for itself. So Tj has to equal Tk, which goes in, minus Tb, which goes out. Whatever is the difference between Tk that goes in and Tb that comes out has to come out through Tj. So you can directly write the same equation. These are equal, same equation. If you think in that way. And in fact, if you do this, if you really buy into using this shortcut and the next shortcut that we talk about, you can actually skip writing the primary and secondary variables, which I find to be nice. But again, it's whatever you're comfortable with. Don't sacrifice accuracy for speed here. The shortcut's not great if you're not super comfortable with it. So if you ever get confused, if you're like, I don't remember how to use this sort of reasoning with the shortcut, you can always go back to just summing everything that goes into the contour and you're good. Okay, so that gave us a continuity equation associated with J of Tj equals Tk minus Tb. So Tj equals Tk minus Tb. And we place it in the row associated with J because it's the continuity equation associated with element J. Great. So neither K nor B has a continuity equation because they're links. They're not branches in the normal tree. So we're going to need to write instead for them compatibility equations, which is the next part. 1G. And for that, we go back to our instructions. It says we write one for each passive link by temporarily including it in the tree, in the normal tree, and finding the compatibility equation for the resulting loop. Solve for the secondary across variable associated with that link. So we go back up here and we say we have two links, K and B. We have to write one for each. So I'll use orange here. And we could take either one first. Let's take K first. And we're going to temporarily include K here into the normal tree, creating this loop. And we need to write the loop equation, or what is essentially the KVL equation for that loop, using across variables. So if you just start anywhere and you go around, you say, okay, drops will be positive, gains will be negative. Then you start here, you go positive omega K drop plus omega J drop. You follow the normal tree branch. And then you're going to gain here, so it's minus omega S equals 0. So you then solve for the secondary variable associated with K, which is omega K. So that tells us that omega K equals omega S minus omega J. Again, there's a sort of shortcut. If you think of these edges or these elements as being vectors that take us from this node, the tail node, to the head node, so from here to there, if you think of K as being that vector, which we'll represent with omega K, so omega K takes us from here to there. If you follow a different path to get here, it has to be equal to omega K. All right, so we can say omega K is equal to, we can start at the tail and follow another path to the head and sum them up. So we'll sum up the drops. Omega S is a drop, and then omega J is a gain, so minus omega J. And these two are the same equation, and either route you took gets you there, no big deal. If the shortcut way doesn't make sense, just go back to sum drops around a loop, solve for the secondary variable. If you do the shortcut method, in both cases, you end up with the secondary variable on the left-hand side automatically. And so you can identify them sort of as you go instead of at the beginning. It's up to you, though. So we said this compatibility equation, it was omega K equals omega S minus omega J. Great. Now, we're to our last compatibility equation, and that's including this guy in the normal tree, which creates this loop with J. So you could sum them. It would be omega B minus omega J equals 0. which tells you that omega b equals omega j. You also could recognize that this is just like when you have two elements in parallel in a circuit. They share the same voltage. In this case, they share the same, what's the across variable here? Angular velocity. They share the same angular velocity. So you could just say omega b equals omega j. Great. Now we are at the point where we've finished 1 in our procedure, and now we're ready for 2, which is to eliminate variables that are not state variables or input variables and their derivatives. The following procedure is recommended. So the first thing we do in A is eliminate all secondary variables by substitution into the elemental equations of the continuity and compatibility equations. And if we set it up like this in this table form, we can literally just do this substitution straight across to eliminate all the secondary variables in one nice substitution. And this is guaranteed to work every time, which is pretty nice. So 2a, we can rewrite our j, k, b elemental equations with the substitutions. So omega j dot equals 1 over j. Instead of tj, we have tk minus tb, substituting in the purple equation. For tk, or for k, we have tk dot equals k. Instead of omega k, we substitute in omega s minus omega j, the first orange equation. And we've got that equation. And then finally, tb equals k, or b. Instead of omega b, we substitute in the second orange equation, omega j. So we have contracted this set of 6 equations down to a set of 3 equations. We need to get it down to 2 equations. The system order is 2. Got to get it down to 2 equations. We have to eliminate one more equation and one more variable, and that's tb. Okay, so you got to get rid of everything that's not a state variable or an input. Omega j, tk, those are both state variables. Omega s is an input, so we're left with tb to get rid of. And conveniently, we can do that by a simple substitution, which lets us go from these equations to the set of equations omega j dot equals 1 over j tk minus, instead of tb, it's b omega j, and tk dot, the second equation, is the same as it was, k omega s minus omega j. We didn't need to get rid of anything in it. Input, state variable, state variable. So these are our state equations. This was actually 2b. And so we're ready for 2c, which is to write the state equation in standard form, and then also the output equation we'll write in standard form. So first off, we want to write the state equation in standard form. Standard form is x dot equals the A matrix times the state vector x plus b times the input vector u. And let's go ahead and write that out then. That's going to be x dot is omega j dot tk dot, referring back to our order that we chose x to be in, which is up here, right? So omega j dot tk dot is what we just wrote. So that's x dot equals the A matrix, which it has to yield a 2 vector, and it has to operate on a 2 vector. So what dimension does it have to be? It's multiplying the state vector, which is omega j tk. So this dimension, the inner dimension, has to match, right? So it's got to be a something by 2 times a 2 by 1. So it has to be a something by 2 at least. What is the first dimension? What does it have to be? 2 as well, because it has to give you a 2 vector. So it's a 2 by 2. Plus the B matrix, which again has to yield 2, so its first dimension has to be 2, times the input vector U, which is a 1 vector, so 2 by 1 is the dimension of B. So I'll put that. Okay. So our now we've got it set up. We can just transcribe these 2 equations in here. So the first equation will be in the first row because it's the omega j dot equation. Omega j dot equation equals, we have to figure out what is the coefficient of the first state variable, omega j. Well, negative b over j is the coefficient of omega j. So negative b over j goes in this element because when we do this multiplication, negative b over j multiplies omega j. The tk coefficient is 1 over j, because when we multiply this matrix by this vector, this component multiplies this component. So 1 over j tk. And there's no omega s term in that equation, so 0 omega s. All right, now we've got the tk equation. We have negative k omega j. So negative k, the omega j is here. There's no tk term, so 0. And the omega s term is just coefficient k. So if you multiplied all this out, it would look just like this, but with the vectors, right, on each side. So that's our one of our answers, I guess. This is if we're looking for a state space model. This is the state equation. The output, before we write it in standard form, we need to write the outputs in terms of state variables and inputs. The output vector, we said, was equal to TK HJ, right? We said it was the torque through the spring and the angular momentum of the moment of inertia. So to write each of these in terms of their state variable and input representation. So TK is already a state variable, right? So we can just say the identity TK equals TK. Already a state variable. We can say for the angular momentum, which is not a state variable, what it is in terms of state variables. So the definition of angular momentum is frequently given as the moment of inertia times the angular velocity of the inertia. So this happens to be a state variable, so we're good to go. And we are ready to write it in the standard form, which is C matrix X plus the D matrix times U. Again, we can expand these if we like. We could say TK HJ to help us fill in the matrices when we expand it like this. The C matrix has to yield a 2 vector. It multiplies X, which is a 2 vector. The state vector X being omega j tk still. And the D matrix has to yield a 2 vector. It has to multiply a 1 vector, so it's a 2 by 1. Although it does occur in this case, the A matrix and the C matrix need not be the same dimension. They do have to share a second dimension that's equal because they both multiply the X vector, but you could have more or fewer outputs than state variables. They happen to be equal in this case. So the C matrix does happen to be a 2 by 2, But it's not always going to be a 2 by 2 when you have an A that's a 2 by 2. This is an accident, so don't read too much into it. So we've got this output equation. We're ready to fill it in. The C matrix, we're going to transcribe this first equation into it. Tk equals Tk. So 0 omega j, 1 Tk, and 0 omega s. The second equation is Hj equals j omega j. So there's a j omega j, 0 Tk, 0 omega s, and we have our standard form of the output equation. So we could put like output equation. This would be the state equation. So that is that's our state model, and we've got a second order model. We got to figure out what those coefficients are. J and K pretty easy to figure out. B is a little more challenging, but there are ways to do it. Some of them experimental, some of them you could maybe look up in the manufacturing catalog for that, or spec sheet for that part. So that's what we've got. Any questions on this example? Okay. I mean, you take a sort of bird's eye view of it. This is what this whole portion of the course is all about. Taking some sort of like engineering sketch, turning it into a lumped parameter model, turning that into a linear graph model, turn that linear graph model into a state space model. That's what we're doing. So this is a very important skill to be able to do, to go from there to there. All right. Well, good work, guys. Have a good weekend. Keep it real out there. Be safe, and I'll see you next week.
Okay. Do you have a second for a quick homework question?